So this is the course, the advanced course in classical logic. For one term, one semester. And it has two main parts, classical propositional logic and classical predicate logic. And we will take some topics that are not covered in the standard courses. Some additional material that is usually not studied in the standard courses. So we will start, of course, with the first part, classical propositional logic. Perhaps it is the simplest logic. But even in this logic, there are some questions that are still open, and some questions that are quite difficult, some computational questions, some questions about axiomatization, and so on. So even for this logic, there are some open problems. So this first lecture is just a reminder of what you know from standard courses, and we will have also some new material. So we will recall what is the syntax and the semantics of the classical propositional logic, recall its axiom system and completeness of this axiom system, and some properties of this classical logic, like compactness, decidability. We will consider some new stuff like interpolation theorems. There are various different interpolation theorems. And at the very end, I will briefly review some interesting properties that are usually not discussed in courses, but maybe they may be interesting to beginners. So, of course, we remember that in the classical propositional logic, we build formulas from variables. They are called propositional variables. So they denote some propositions. For example, it is snowing today is a proposition. It can be either true or false. What are not propositions? For example, questions. Why do you live in Moscow? It is not true or false. It is a question. We can connect propositions or statements by connectives. In propositional logic, we have some standard connectives like negation, not, conjunction, conjunction and disjunction or implication. So if then, usually this is the standard set of connectives. Sometimes we add equivalence, but usually equivalence is a abbreviation. So you can define it from the previous connectives. And of course, these connectives are not independent. You can define disjunction in terms of negation and conjunction, and so on. Moreover, we can define all connectives from just one connective. But this is exotic from the viewpoint of building axiomatic systems, from the viewpoint of reasoning in this logic. So we will use the first 4 connectives. And we also, so negation is the unary connective. All other connectives are binary, so they take 2 arguments. And we will also have nullary connectives or constants, true and false. Of course, you can define them, but we will introduce them in the language. And in formulas, we will also use parentheses. Okay, so formulas will be built by induction. So the simplest formulas are true and false and variables. Each of these symbols is a formula. Now, if you have already a formula A, then not A is a formula. You don't have parentheses here. You don't need parentheses here. And if you have 2 formulas already built, A and B, then you can build formulas A and B, and A or B, A implication B, with parentheses. For unique reading of formulas, you need parentheses here. Okay. Okay, so this long definition can be rewritten shortly in this one line. Well, this is related to some stuff from grammar theory of mathematical grammar. This form is called Bekosnauer form. So normal, some representation of a grammar in some normal form, in a compact form. So it is read as if you have A and B already formulas, then you can build true, false, variable, and here you also use use A and B as meta variables for arbitrary formulas. Okay, so the set of all formulas will be denoted by Fm. The question is, what is the cardinality of this set? Of course, it is infinite because you have infinitely many variables, but what is exact cardinality of this set? So the question to the students.
Евгений Евгеньевич, звук пропал опять.
Да. Okay. So this set is countable. The answer is on the slide. So we have, so each formula is a string of symbols in a countable alphabet. You can find say it is in a countable alphabet or in finite alphabet if you write this index I as a number in decimal notation, for example, or in binary notation, then you will have a formula is a word in a finite alphabet. But of course, there are countably many words in the finite alphabet. Okay. So this is semantics. This is the syntax, how to write objects. In our case, objects are formulas. Now, how to understand them? What is the meaning of formulas? For this, we introduce a valuation or assignment. Sometimes it is called assignment. So to every variable, we assign 0 or 1. So 0 stands for false, 1 stands for true. And then this function v is extended from variables to all formulas by induction. Our formulas were built by induction, and evaluation is extended to them again by induction. And many proofs are carried out by induction. So for true and for false, this is always the same. True is always evaluated as 1. False is always evaluated as 0. For negation, of course, we know 0 turns into 1, 1 into 0. And for other binary connectives, we know the tables. They're called truth tables. Familiar to all listeners, I believe. So we extended this function v to all formulas. So for some formulas, so if v is some particular valuation, then for every formula, we have a value 0 or 1. So if the value of some formula is 1 for this particular valuation, then we say that this formula A is true under this valuation v, and write this symbol. And otherwise, we call that it is false, and write this symbol. So on the particular valuation v, some formulas are true, some formulas are false. And moreover, we have negation that maps true formulas to false and vice versa. So all formulas are divided into exactly two subgroups with true and false for every fixed valuation v. Let us recall this important notion and result. So if we have a function with n arguments from 0, 1 to 0 and 1, they are called Boolean function. Then we can say that some formula A expresses this function. This means that if we build the truth table for A, so all values for different values of P1, Pn, then we obtain exactly the function f. Of course, many different formulas may represent the same function. Even infinitely many formulas may represent the same function. So P or Q, Q or P have the same truth table, so they represent the same function from 0 and 1, namely this function. Okay. So our theorem says that we can express every Boolean function with some formula. And in formulas, we used negation, conjunction, disjunction, implication. Of course, we don't need so many connectives. Negation and conjunction are sufficient. Negation and disjunction, false and implication are sufficient. An important set of connectives is one conjunction and plus modulo 2. So plus, so this is like a plus in numbers, and conjunctions works like a multiplication. And therefore, you can write polynomials in this basis. So you can write x1, x2, and x2, and not and x1, x2 plus x1 plus x2 plus 1. So this is a polynomial of degree 2, and so on. And the theorem is that we can express every function as a polynomial in this basis. There are two special connectives, Schaeffer stroke and Pearson's arrow, that again have this property that every function can be expressed, because you can firstly express conjunction, and then negation, then conjunction, and then all other stuff. The question is, if we take some finite set of connectives, finite set of Boolean functions, we can ask the following question: can we express all functions from this finite set? So a system of Boolean functions, for example, a finite system of Boolean functions, but their theorem works for arbitrary sets of Boolean functions. Functionally complete means that we can express all functions, all Boolean functions from this set, like we did here. And perhaps you remember this classical result from the course of discrete mathematics. So as this set is functionally complete, you can express all functions if and only if this set is not contained in the five main classes. T0, the class of functions that preserve 0. So if you put all arguments 0, then you obtain 0. Similarly, T1, functions that preserve 1, or truth preserving and false preserving. The class of linear functions, so Boolean functions with n arguments that can be represented by polynomial of degree 1, of linear polynomial. The class of monotone functions. So if arguments are bigger, then the value is bigger or the same, less or equal in both cases. For example, disjunction and conjunction are monotone operations, but implication is not. And self-dual function. So if you substitute negations of arguments into the function, then you obtain the negation of its value for all x1, xn from 0 and 1. So these are 5 classes. They are called pre-complete classes. If your set of functions is contained in some of them, then it is not functionally complete, because you can only obtain functions from this class. But if it is not contained, if you have at least one function that is not in T0, at least one function not in T1, and so on, then your class is complete. Clearly, of course, Schaeffer's stroke and Pearson's arrow does not belong to any of these classes. And therefore, it is complete. It is functionally complete. Okay, so is it clear? Are there any questions? Okay, let's proceed. So if we have a formula and it is true always for all valuations, then we call it valid, or there is another word, A is a tautology. So it is always true. A formula is satisfiable if it is true sometimes. So there is a valuation for which it is true. And of course, we have a clear connection between these two notions. A formula is tautology if and only if its negation cannot be satisfied. If A is always true, then its negation is always false, so it is never true for no valuation. It is convenient to extend these notions to sets of formulas, some of these notions. So if we have some gamma, some set of formulas, finite or infinite, firstly, we extend this notation. This set of formulas is called true under the valuation V if all formulas are true. If V of A is 1 for all formulas A from our set gamma. So gamma is true under this particular valuation V. Of course, we could consider the notion gamma is valid, meaning that all formulas are valid from gamma, but this is not a very interesting notion. So this only means that all formulas are valid. So it reduces to the property of each particular formula. But satisfiability is extended to the two sets of formulas. This is a non-trivial notion. A set of formulas is satisfiable if there is a valuation for which all formulas from gamma are true. So we need to have one valuation that makes all formulas true. So they exist for all. So that is a notion of a kind that exists for all. And another important notion is that this set of formulas implies, or sometimes it is called entails, a formula A. So from gamma, formula A follows, logically follows. In other words, A is a logical consequence of gamma. So this means that for every evaluation such that gamma is true in this evaluation, A is true. And usually when we solve some tasks, we take some set of formulas. For example, Pete said the truth, Kate said the false, some statements about real objects, and then somebody asks, does this statement follow from our assumptions? So can we deduce, can we obtain a consequence about some statement A from our assumptions? So this is the main reasoning task in logic. If we take some assumptions, then we obtain some consequences. Can we obtain some consequences from this assumption? Again, the same connection like here. Formula A follows from gamma if and only if we take negation and put it into the set of gamma, then this set is not satisfiable. So this is a clear analogy from with this fact. Of course, if gamma is empty, we obtain exactly this old fact. Okay. Okay, let's have some interactive part. Can anyone say, is this formula a tautology?
No, well, it looks like a tautology. If we evaluate variables P and Q in any way, we still can get true.
Yeah. So if P is true, then this implication is true. If P is false, then this implication is true. So it doesn't matter. We can even put Q here and another variable R here and still get a tautology. Yes, quite an unexpected tautology, I would say. Let's consider this set of formulas. Can we say that is it satisfiable or not? Can we assign zeros and ones to variables? To simplify the task, notice that not P or R is the same as P implies R. So this is an application, in fact. And similarly here. So we have P implies R, S implies P. So S implies P, P implies R. And also S implies not R.
It seems like it's not satisfiable.
So from these two, we have, so S implies P, P implies R. So S implies
Yeah.
R. And we also have S implies not R. At the first glance, you can think that this is impossible, that S implies R and S implies not R. But is it really impossible?
I think if we evaluate P as 0, S as also as 0, and R as, well, something else, I don't think that's matter. We have that the first formula is true, the second is also true, and in third we have a 0 in
premise. So this is premise.
in
and
premise,
conclusion.
and we also have a true. So it's, yes, it's satisfiable.
Yeah, so we have S implies R and S implies not R. But this may happen when S is 0. So we need to say that S implies 0. I didn't write the answer to this. Yes, yes. So S is 0, and then here we have 1. Here we have 1 because not S is 1. And to make this true, you can either put R true or P false. It doesn't matter. After our analysis, we can even simply ask the following, answer the following question. Does this set imply not S? So from this set of gamma, we necessarily have that S implies P, because it is simply this formula, equivalently rewritten. P implies R, and therefore S implies R. But we also have S implies not R. What do we have then? Does this imply that not S?
Well, yes, because if we have just S, it is like we have a contradiction.
Yeah, so it is impossible to make this set true if we assign 1 to the variable S. Because then S implies something R, and S implies something not R. If S is 1, then at least one of these will be false. So any valuation that, every valuation that makes this set gamma true has the value 0 assigned to S. And if we think, does this set implies P, then no, because we remember we can assign 0 to S. We have to assign 0 to S. Then this formula is true, this formula is true, and this here we have a freedom either to put 1 to R and then any value to P. So we can put 1 to R and then P can be arbitrary. In particular, we can assign 0 to P. So P does not follow from this set. Okay. Of course, we know that there is an algorithm that checks satisfiability of a formula. If we have a formula, simply check all valuations for variables that are in this formula. If you obtain one, at least one valuation, then yes. If no, then no. So this is an algorithm, but you need to check all valuations for variables from A. If A has 100 variables, you will need to check 2 to the power 100 possible valuations. So exponentially many valuations. So if somebody find the polynomial algorithm for this, then you will get $1 million, because this is the problem called P equals not P. And if you, on the other side, prove that there is no polynomial algorithm, polynomial in time, then again, you will solve this problem, one of the 7 millennium problems. Okay. From the standard course, of course, we know this axiomatic system. Usually it has 10 or 11 axioms. I also put here the axioms for truth and false. There are some variations, especially for the axioms for negation 7, 8, and 9. There are some different axioms in different textbooks. So these are axioms, and this is the rule of inference. Just one rule of inference. And if you drop the the axiom number 9, you obtain the Interestingistic propositional logic. This is another logic, another propositional logic that is quite important in the in mathematical logic. Perhaps you remember the notion of provable formulas in a calculus. For example, this calculus. So a formula is called provable or derivable, or a theorem of this classical propositional calculus. So CPC stands for classical propositional calculus. If there is a derivation or a proof or an inference, sometimes called in this calculus, in which this formula is the last formula. And what is a derivation? A derivation or a proof is a finite sequence of formulas in which every formula is either an axiom or is obtained by some rule from previous formulas. Previous in this list, in this sequence. So from some Ci and Cj, where I and j are less than k. Here I give some short proof or derivation. So we derive that A and B implies A or B. So we have this axiom, this axiom. These are exactly the axioms from our system. We also take this long axiom. This is an axiom of the form alpha implies beta implies alpha, where alpha and beta are these long formulas. Then we, by modus ponens, obtain this from 1 and 3. But 2 and 4 are not from 2 and 3. Sorry. Now we want to obtain use 1. And here we have A and B implies A. And here A and B implies that A implies what we need, disjunction. In order to put these formulas together, we need a very long axiom of the form 2. This is the second axiom of our system. And then we use 2 modus ponences and obtain the result. So even short formulas may have long proofs, long in different aspects. It may have many steps, and it may have quite long formulas in the derivation. Okay. So a well-known theorem, we will not prove it here because it is already proved in the standard courses, that this axiomatic system is complete. So we prove a formula if and only if it is a tautology. This is called simple completeness or weak completeness. And in particular, we obtain that the classical propositional calculus is decidable. What do I mean? So if we have some axioms and some rules, we can pose the following question. Take a formula. Can we decide whether it is provable from these axioms or not? The only thing we can do is to build proofs one by one until we obtain our formula. But we have no guarantee that we will finally obtain a derivation, or if this formula is not provable, it is not clear when to stop. But this completeness theorem connects this derivability or provability with the notion of tautology. And we know that there is an algorithm that checks whether a formula is a tautology. So we automatically obtain decidability. So this means that there is an algorithm that takes a formula and returns yes if the formula is a theorem, and no otherwise. Derivation of a single formula is not very interesting. A more interesting task is to derive some formula from a set of assumptions or hypotheses. So if we have a formula A and a set of formulas gamma, then we similarly introduce the notion a formula is derivable from gamma, from a set of formulas gamma, if it has a derivation. So red pieces are new. So all other stuff is the same. So now we derive formulas from a set of formulas gamma. And what does it mean? So a derivation of a formula from a set of formulas gamma is again a finite sequence of formulas, such that each formula is either an axiom of our calculus or belongs to gamma. So we can use our hypothesis. So in this context, formulas from gamma are called hypotheses, or again obtained by modus ponens. So this was a completeness theorem from our previous slide. And this is a new completeness theorem, a strong completeness. So a formula is derivable from gamma or provable from gamma if and only if it follows logically. So for every valuation V, if gamma is true under V, then A is true under V. So our axioms not only allow us to prove all tautologies, but they also allow us to prove all consequences from all possible sets of hypotheses gamma. Quite an interesting property. Okay. From this completeness theorem, strong completeness theorem, the following important fact follows. It is called compactness. If A follows from gamma, where gamma is possibly infinite set of formulas, then A follows from some finite subset. So this statement is about formulas and evaluations. We don't have any axioms here, don't have any proofs here, any derivations. So here we only deal with the notion formula is if for every evaluation V, gamma is true in V, then A is true in V. So we speak about evaluations here. But since we have strong completeness, we can go from this consequence symbol to the derivation symbol. So if gamma implies A, then from gamma we can derive A. But what is the derivation? A derivation is a finite thing, is a finite set of formulas. A finite derivation can only use finitely many formulas from gamma. Therefore, A is provable from a finite subset gamma. And then we get back to the consequence law symbol. Another form of compactness, an equivalent formulation. If every finite subset of formulas is satisfiable, then the whole set gamma is satisfiable. So if you have infinitely many formulas and each finite subset is satisfiable, then the whole set of formulas is satisfiable. And again, this follows easily from the first theorem. So this is just an equivalent formulation because gamma is unsatisfiable if and only if gamma implies false. So if gamma implies false, then there is no evaluation for which gamma is true, because then false would be true. False would have the value 1, which is impossible. And vice versa. This is easy equivalence. And this equivalence allows you to obtain this theorem 1 from theorem 2 and theorem 2 from theorem 1. So these are easily equivalent formulations of compactness. Okay. But if we did not know the completeness theorem, it is not quite clear how to prove this result, compactness. So the task is try to prove this compactness, for example, the second one, without using the axiomatization. So we start with an infinite set of formulas, and we know that every finite subset is satisfiable. For example, every subset of this form, A0, n, the first n plus 1 formulas, each of them is satisfiable. So there is a valuation V sub n, Vn. But then we need to combine all these valuations into a single valuation where gamma is true. So the task is try to guess how to build one valuation from many valuations Vn that have this property. This is not quite an obvious statement at the first glance. Okay, now let's go to some new stuff. Craig interpolation theorem. So in this theorem, we build some, if we have some implication, we build some formula in between. But this is easy if we don't have any other restrictions. For example, we can take B as just A or just C. But we have an additional restriction. The formula B must have variables that are both in A and in C. So var B is the set of variables that are in the formula B, that occur in the formula B. So if we have some implication that is valid, that is provable in our calculus, and they have some common variables, then we can build one formula with these common variables such that A plus B and B plus C. For classical propositional logic, this theorem is quite simple. In fact, Craig proved this theorem for classical predicate logic, where you have quantifiers, you have predicates of different arities, functional symbols, constants, and so on. But here it is very simple. So let us just analyze which variables are in A and in C. So A has variables P and Q, some lists of variables P and Q. C has variables Q, and let us, for simplicity, assume that it has only one variable S that is not in our formula A. For many variables, the proof is the same. But for simplicity, we will write proof for just one variable. So in our theorem, we have an assumption. A implies C is a tautology. So it is true for all. By the way, so the theorem is about provability, but we know that we have completeness, so we replace probability with this consequence symbol. So we will talk about formulas that are tautologies. Of course, if we think about this theorem as a theorem for our axiom system, this theorem is not trivial at all. And there are many axiomatic systems that do not have interpolation property. But here we replace probability with this consequence. And so we will say, so our assumption is A implies C is a tautology. It is true for all valuations. We have one variable S here that is not in the formula A. Let us substitute true and false for S. Then we obtain two formulas. They are again tautologies, of course, because the first formula was true for all valuations. So these two formulas are tautologies, and by a simple combination, you obtain that A implies conjunction of these two formulas is again a tautology. Let us denote this conjunction by B. This formula B has exactly variables that are common to A and C. And we already know that A implies B is a tautology. It only remains to prove that B implies C is a tautology. So why B implies C is a tautology? B has only variables Q, C has variables Q and S. Why is this formula true for all valuations? Let us substitute some value for C, for S. But of course, we cannot substitute 0 or 1. We need to substitute these symbols, true, false, and true. So let us substitute false. But then we simply obtain a tautology of the form alpha and beta implies alpha. So this formula will be true for all valuations of the variables Q. And similarly for substitution T, truth for S. So this formula is true for all valuations. If we substitute true for S, we obtain a tautology. If we substitute false for S, we obtain a tautology. And you can easily get, so this is the end of the proof. That's it. Moreover, we build constructively an interpolant, a formula B. And if we had many variables S here, of course, we will need to take all possible substitutions of false and true. So if we have C with many variables S here, then we substitute true or false for every of these variables and obtain a long conjunction. You can see here that the formula B, the interpolant, may have quite a long length. So it may be exponentially longer than the formula C. And in fact, if you think a little, you can find out that this construction is the strongest interpolant. There may be many formulas B that are interpolants for A and C, but this particular is the strongest one. A simple task is try to build the weakest by similar manipulations, but with the formula A, not C. So anyway, we proved Craig interpolation theorem. But Craig interpolation theorem is not the only interpolation theorem. There are also other variations on interpolation. Lyndon proved a stronger version, again for classical predicate logic with quantifiers, with predicates, and so on. There is also a uniform version of Craig and uniform version of Lyndon interpolation. Lyndon interpolation is formulated easily, but we need an additional thing. In every formula, we have some variables, but some of them are positive and some are negative in some sense, in the following sense. So previously we denoted var A by var A, the set of all variables, but now we will have some variables positive and some variables negative. So we will introduce var plus and var minus. In the formula true and false, we have no variables. So empty. In the formula pi, in the variable, we have only one variable and it is positive. It occurs positively. And we have no negative occurrences here. So if we put negation, then all positive variables become negative, all negative become positive. And for conjunction, and similarly for disjunction, positive variables of A are positive variables of the whole formula, and positive variables of B are positive variables of the whole formula. And similarly for negative, and similarly for disjunction. And I could even stop here because implication can be expressed in terms of negation and disjunction. A implies B means not A or B. So you can figure out which variables are positive and negative in implication. But let us write it explicitly. What does it mean? Positive variables of implication. So in implication, A, the formula A is in negative part, and the formula B is in positive part. Therefore, we take negative variables of A and positive variables of B and take the union. And similarly for negative, exactly the same. Let us again have an interactive part. This is a formula. P implies Q implies P implies S. What are positive variables of this formula? So this formula is an implication. It has a positive part and a negative part. Its negative part is again an implication, and so on. So this variable S, is it positive or negative?
Well, it's obviously positive.
So S is positive. The peculiarity is that we will have, so it is not that a variable is positive or negative, but a particular occurrence of a variable is positive or negative. So here we have P here and P here. They may be different. Some of them may be positive, some negative, or maybe both positive or both negative. So everything may happen. So S is positive clearly. So this implication is negative, but it is again an implication. It has a negative part here. Therefore, this P becomes positive. So we have S positive, this P positive, and these two
This is axiom, yes. P imply Q imply P.
Well, this is an axiom, but this doesn't matter in this task.
No, we can say what it is true. So it is while negative of true is empty set. No.
Well, in this task, we do not have any true or false. We have only a formula. We have only some connectives, some variables, some parentheses. And that's it. We don't even know what this formula mean. Well, for classical logic, of course, it is this premise is a tautology, but we don't work with classical tautology here. With classical logic here, we work only with just syntactic objects, just formulas. Значит, давайте некоторые пояснения. Мы здесь разбираем просто вот запись самой формулы синтаксическую и смотрим на вхождение переменных. Какие переменные там находятся в позитивной позиции, какие в негативной, да? Мы совершенно ничего не знаем про оценки переменных, про то, что есть какие-то там тавтологии и аксиомы для тавтологий. Сейчас просто разбираем формулу на кусочки. Значит, формула имеет вид что-то влечет что-то. Значит, вот это как бы А и какой-то там С, стрелочка D. Смотрим, как у С, стрелочка D проверять, какие переменные позитивные, какие негативные. Значит, от заключения надо взять все позитивные. Ну, смотрим, какое тут заключение? S. S это просто переменная. И она, собственно, позитивная. Вот написано здесь, да? А негативных нету. Значит, S будет точно позитивным. Вот это вхождение буквы S будет позитивным. Хорошо. А вот все, что здесь надо будет как бы инвертировать. Если сейчас мы найдем здесь позитивные вхождения, они для нас будут для большой формулы негативными и наоборот. Значит, здесь эта формула тоже имеет вид импликации. Разбираем. Вот это ее негативная часть, а это позитивная. Q плюс P. Q влечет P. Значит, вот это для вот этой маленькой формулы, которая в скобках, вот эта буква P была бы отрицательной, да, она вот. Но для нашей большой формулы, раз это все содержится в посылке, то это будет P позитивная. А вот эта часть, она, наоборот, для этой маленькой формулы, она позитивная. Ну, а для нашей большой, соответственно, они пойдут как отрицательные. В ней смотрим. Тоже есть отрицательная часть и положительная часть. Раз вот эта часть положительная, она и для вот этой вот большой тоже положительная, а для нашей все отрицательные. Значит, вот это P у нас пойдет в отрицательные. А вот это Q пойдет в положительные. Ну, соответственно, раз она в противоположной стороне. Таким образом, у нас позитивными, вот в этой всей формуле, положительными вхождениями будут переменные PQR, PQS, тут никакой R нету. А отрицательным что будет? Значит, кто проследил за моими рассуждениями?
Ну, P.
Да, одна только P. Ну, можно, вот тут можно было бы, как сказать, более такую мультипликацию сделать. Ну, у меня статическая. Мы как бы всем вхождениям приписываем, на каком они месте находятся. Как бы вот эта вся подформула, она положительная, ну и она состоит только из подформулы S, только поэтому плюс. Это вся минус, поэтому когда мы будем анализировать и расставлять там плюсики, минусики, для нашей, надо их менять. Значит, она имеет вид импликации. То, что слева, оно отрицательно. Но это отрицательно для нее, для маленькой формулы, а для всей большой положительно. Поэтому надпись ставим плюс, а вот эту разбираем отдельно. она тут положительная, а для всей нашей огромной формулы она отрицательная, поэтому будем менять. Значит, Q стоит слева, значит, она минус, а справа P, значит, плюс. Но это только для маленькой аппликации, а для нашей большой мы помним, мы должны менять все. Значит, наоборот, плюс и минус. Вот, если тут не ошиблись, да, P, Q, S в плюс попали, а P попало в минус. Так вот, so, Lyndon interpolation. So, if we have A implies C, then there is a formula such that A implies B and B implies C are tautologies. But we need to be more careful about variables. Formula B has variables that are common to A and C. But some variables are positive here in B and some are negative here. And we will require that for positive variables from B are those that are positive in A and positive in C. And similarly for negative. So this is a stronger requirement, therefore a stronger theorem. But we will not prove it here because we need to be more careful about positive and negative occurrences. And to prove this theorem, for example, you can use a sequent calculus. Okay. Uniform interpolation is much easier to formulate. So if you have some formula A, so in the usual formula, in the usual interpolation, you have for every A and C, you build an interpolant B. Here, we will build one interpolant B that serves for all formulas C of some specific kind. So we just take some variables from A, and for them, we build some formula B such that, of course, B should be a consequence of A. And secondly, this B is an interpolant for all formulas C. So for every formula C such that A implies C is a tautology, and their common variables are among this list Q, we have that B is in that interpolant. So A plus B we already have, so B implies C. So this B is just one interpolant for all formulas C that have the form Q, that have the variables Q and some other variables not from A. Just one interpolant for all formulas. Quite an interesting property. And again, this can be proved for stronger logic, not only for propositional logic. But again, the proof here is simple. I will only give a sketch of a proof. So for this formula, we take all formulas of variables with variables Q such that A plus D is a tautology. But you can say there are infinitely many formulas with variables Q. Even with one variable, for example, R, you can build infinitely many formulas. For example, R, not R, R and R, R implies not A, R, and so on. The question is how can we take a conjunction of all these formulas? But, so there are infinitely many formulas, but there are only finitely many pairwise non-equivalent. Many of them will be equivalent, so we can just take one formula for each equivalence class. So if Q has n variables, there are at most 2 to the power n non-equivalent formulas. And so we can take just one formula for each equivalence class. And now it is an exercise prove that this formula is exactly what we want. It satisfies these two conditions. Well, condition one, of course, is simple because all formulas D are consequences of A. Therefore, their conjunction is a consequence of A. So B is just one of the formulas D, in fact, because B is also a formula of the variables Q. So it is one of these formulas, in fact. Anyway, so item 1 is easy, so you only need to prove item 2, which is just an easy exercise. And you can prove Lyndon uniform Lyndon interpolation. So you will need to take care of positive and negative formulas in A, in B, in C. As an exercise, try to formulate carefully the uniform Lyndon interpolation theorem. I will not go into details here. And the last stuff, some interesting properties of classical logic, of classical calculus in particular. For example, so first, if we remove this axiom, the law of excluded middle, we obtain the interestingistic logic. It is, again, quite a nice logic. It has, it is decidable, it has compactness, decidable, but its complexity is higher, slightly higher. It has compactness, it has interpolation, correct interpolation, uniform interpolation, and so on. What if we remove disjunction from our language? We only build formulas from negation, conjunction, and implication. How can we axiomatize all tautologies in this restricted set of connectives? The answer is simple. Just take from our axioms, just remove these axioms about disjunction, and you will again obtain a complete system. It will allow you to prove all tautologies with negation, implication, and conjunction. So a kind of modularity. So this axiom system, if you remove some part about some connective, you obtain again a complete system for the remaining connectives. Similarly, we can remove conjunction and leave only disjunction. And again, just take this corresponding axioms. Moreover, we can remove both conjunction and disjunction. We can have only negation and implication, and simply take the axioms for implication 1, 2, and for negation 7, 8. And you will obtain a complete system and bonus, of course. 7, 8, yes. And you will obtain, you will be able to prove all tautologies that use these two symbols. And what about just one implication? Of course, you can say that this just one implication is not a functionally complete system. You cannot express all Boolean functions from just implication, because implication preserves one. One implies one is one. But nevertheless, you can ask the following question. Just take one implication. You can build formulas using just implication. Some of them are tautologies. Can you write axioms that are sufficient to prove all tautologies? And the rule modus ponens. The rule modus ponens, of course, is we have this rule. It uses implication. So we have the rule modus ponens. We only need to write axioms. And you may think that perhaps in this system, just take axiom 1 about implication and axiom 2, and this will be sufficient. The answer is no. These two axioms are not sufficient, are not enough to prove all tautologies that use implication. You also need an additional axiom. This axiom is called Peirce's law. Закон Пирса. A plus B plus A plus A. So only if you add this axiom, to 1 and 2, to the axioms 1 and 2, you obtain a complete system. And the proof is not trivial, because you do not have negation. You can't define what is a maximal consistent set of axioms, of formulas, and so on. So the standard proof doesn't carry out. The question is, but if we don't want to take this Pearson's law, what do we axiomatize? Axiom 1 and 2. What do axiomatize axiom 1 and 2? The answer is that they axiomatize only implicational theorems of interstilistic logic without the law of excluded middle. And again, to prove this is not an easy task. Okay. Now the question is, in our axiomatic system, we had many axioms, 10 or 11 or 12 even. But can we axiomatize all tautologies, for example, for this one connective, with just one axiom? So we had three, for implication, we had 3 axioms, axiom 1, axiom 2, and Pearson's law. But can we do the same with just one axiom? And the surprising answer is yes, we can. Quite an old result. This is just a very long axiom. Well, it is not quite long, but still. So quite an interesting axiom. It has D only once. A is 3 times, C 2 times, B only once. So, and if we want to do the same for the interstilistic model, for the interstilistic logic with one implication, again, this can be done, but the axiom is even longer and even more complex. And the proof, of course, is not very easy. But still, this can be done. Moreover, you can do the same for negation and implication. You can write quite a long axiom that axiomatizes all tautologies that use negation and implication, and for other sets of connectives, of course. But it is not quite easy even to find such an axiom, a unique axiom. Another direction. Let us take just one connective, Schaeffer stroke. Can we write axioms and rules to axiomatize all tautologies? We don't have any other connectives. Such an axiom and the rule was found. I did write the author. So the axiom is quite long, and the rule is not very obvious. But still, these two things axiomatize all tautologies. The same of course, can be done for Pearson's arrow. I didn't write it here. Moreover, Alfred Tarski proved a general theorem. He gave a sufficient condition for a calculus that guarantees that this calculus can be axiomatized with just one axiom. And the classical logic satisfies this condition, interstilistic logic, classical logic with implication, interstilistic logic with just implication, and so on. But this is, of course, a harder result. And the final comment, there is a researcher, Ted Ulrich, who collects the shortest possible single axioms. For example, this axiom at the top of the slide is the shortest axiom that can axiomatize all tautologies, implicational tautologies. It has 3, 4, 7 variables and 6 implications. 7 plus 6. You can't do shorter. And he collects many other axioms that have the same property, but have the same length. For classical logic, for Interestingistic logic, relevant logic, and for many other calculus. So this is a page where he puts all this stuff. And the final question. This is the final slide. Try to think of the following question. So in our axiomatic system, we had 10 or 11 axioms and the rule of modus ponens. We will have the same rule, modus ponens. But if somebody gives you another list of tautologies, can you decide whether these tautologies axiomatize all tautologies? Are these axioms enough to axiomatize all tautologies? So we are looking for the following algorithm. It takes finitely many tautologies, and it returns yes if and only if these formulas taken as axioms with the rule modus ponens are enough to axiomatize, to prove all tautologies. So can we build such an algorithm? And if we can, how complex it is? How much time does it take? How much space does it take? So this is just a question to think. And of course, the same question can be put if we just take one axiom. Can we decide whether this axiom is enough to axiomatize all tautologies? And a question in a different direction. Assume that we can write infinite formulas in the following sense. We can write formula, conjunction, and so on. And of course, similarly, we can write disjunctions. Then you can easily define what is a tautology. You can easily define what is the value of this formula under the valuation V. V of this formula is 1 if and only if V of A1 is 1 and V of A2 is 1 and so on. So all formulas must be 1. So the notion of a tautology is can be easily formulated. Now the question is, firstly, how many formulas do we get if we allow countable conjunctions? Will this set of formulas still be countable, or will it have continuum many formulas or hypercontinuum many formulas and so on? Try to find this cardinality. And secondly, now we can express some functions with infinitely many arguments. Again, Boolean functions, but they have infinitely many arguments. The question is, can we express all these functions with these formulas? And of course, more difficult questions. What are the axioms and rules to axiomatize all tautologies in this huge, very, very big language? Okay, so this is the end of the first lecture.